So let's discuss now LSTM in detail in this video. So in the previous video we have seen notations. This is OT, CT is equivalent to OT, HT is equivalent to YT, and this is called as LSTM cell, right? LSTM cell or LSTM unit, right? The CT stands for cell state, right? So and this HT stands for output, right? So now let's try to understand this LSTM cell. Now let us say we have this, the input coming from here is all ones like this, 1, comma 1, comma 1, right? From this FT is equivalent to all ones, right? So this FT is all ones. This is FT. They're all ones, right? And let's say the input coming from here, this one is all zeros, 0, 0, 0, right? Now what will happen, this whatever CT we are getting, this is getting point-wise multiplied here. So we'll get here output as CT minus 1 as it is. If this is all ones, right? So we'll get a CT minus 1 transmitted as it is here. Now if these are all zeros, these are all zeros coming from here, we'll get this CT minus 1 transmitted as it is here, right? That means CT is equivalent to CT minus 1, right? The input if the input coming from here is all ones, right, and if the input coming from here is all zeros, this CT minus 1 gets transmitted through this as it is, right? So CT becomes equivalent to CT minus 1. That means the current cell state is equivalent to the previous cell state. So this is important. Like we are short circuiting this, we are transmitting this CT minus 1 as it is to this to this CT, right? That means previous cell state is becoming the current cell state, right? Okay. Now the other point is, let's say if we have, let's say these are all half, right? So these are all the input coming from here is all halves. This FT is FT, all halves, right? And this is again all zeros. Let's say the input coming from here is all zeros, right? So the input coming from here all zero. Now what will happen in this case? This CT, whatever CT we had here, if the CT was, let's say 2, 4, 6, 8, let's say there are 4 values in this vector and there are 4 values in this vector. Now what will happen if I multiply this with this? So this will get half, this will get half, this will become 1, 2, 3 and 4, right? So this will become this when I do this pointwise multiplication with this vector, right? So that means this CT minus 1 is getting half here at this point, right? And when I have all this 0, this half, this is getting transmitted here as it is, right? Half. So so CT is becoming equivalent to CT minus 1 by 2 actually, right? So this is what. So that means I can decide how much of this input, how much of this CT minus 1 to transmit to CT. I am able to decide here depending on this. I am able to decide how much of this CT minus 1 should be transmitted to CT, whether it should be transmitted completely or halved or 1/4, whatever, right? So I can do that. That's the power I have here. Okay, so that's why that's why you know as I am able to decide how much I am able to how much I should retain in CT from CT minus 1 or how much I should forget in CT from CT minus 1, right? So that's why this operation here, this is called as forget gate here, forget gate, because I am able to decide how much should I forget from previous cell state to this current cell state, right? Because of this pointwise multiplication operation here. Okay, now if you look at the equations here, this FT which is the output of this, This is ft here, this is ft, this ft, we have weight here, we have weight here, right? So these weights are getting concatenated as wf. We are getting one complete weight as wf, this weight concatenated with this weight, so we are getting wf, right? And then we are also concatenating this with this vector with this vector, so this one, right? So this vector is concatenated, or this vector is concatenated with this vector ht minus 1 comma xt. So this is concatenation operation we have discussed here, right? So, and on this product, on this dot product, w and this weight, w weight and this input, right? We are we are adding a bias term here, and on this we are applying this sigmoid function. This sigmoid is applied on the weight from here and here, that is w. Combined weight is called as I'm sorry, wf into this input, right? Plus bias. On this we are applying this sigmoid. That's what ft is, right? So this is what your forget gate, because how much can I forget from this previous cell state to the current cell state, right? Okay, now the next, if you look at here, so this it, this is it is the output of this sigmoid unit applied on this. Now what we are getting here, the weight here is called as wi. The weight here is wi. Weight here is wi, right? On this with this wi, and now what I'm getting here from, I'm getting this ht minus 1 and xt also, right? ht minus 1 and xt, they are concatenated. So ht minus 1 comma xt, concatenation of these two, and the weight wi, right? So on this, with this I'm adding a bias term bi here, and on this I'm applying this sigmoid, and that's how I am getting it. So it is the sigmoid applied on this weight wi and product of weight and ht minus 1 comma xt plus bias term. That's what this it is, right? Now, if we look at this CT tilde, this is CT tilde, right? CT tilde, again, here the weight is WC, weight here is WC. On this weight, with this weight, we are multiplying this HT minus 1 comma XT, HT minus 1 again, comma XT, that concatenation is again coming here, right? Again, that coming here. And on this, we are applying this WC, right? Weight here, this weight will be calling as WC, right? So that weight and plus this bias, on that we are applying this tan H unit now. This is tan H unit, right? So this CT tilde is the product, is applying tan H on this term. Okay, now let's see CT. What is CT, right? Now here, if you look at here, this is the pointwise multiplication of this output coming here, that is CT, CT tilde and IT, right? So this is pointwise multiplication. If you look at this, right? So this is pointwise multiplication. It is denoted like this, right? This is what we are getting here. IT pointwise CT tilde. This is what we are getting from here, right? This one. And what we are getting from here, from here we are getting CT minus 1 into FT, right? So that's what we are getting from here. We are getting this from here. So here we are doing pointwise addition of these two, right? And then we are getting final output CT. So CT is pointwise multiplication, addition of two pointwise multiplication. This one, which is coming from this, right? And this is coming here, right? So that is final output, that is final cell state, right? So computation of cell state is easy. It's done like this. Now let's, so this layer, or this unit decides how much should I add, right? How much should I add to this to this CT, right? So that's why it is called as input gate, right? So this is forget gate, this is input gate, because we are adding here, right? How much, if we put all zeros, that means we are not adding anything. This addition lets us decide how much should I add to this cell state, right? So that's why this is called as input gate. How much of input should I add to this cell state? So that's why it is called as input gate. So here, how much of the previous cell state should we forget or retain? That's why it is called as forget. Okay, now let's talk about the next term, that is OT. OT is again sigmoid applied. This is OWO here. Wait, sigmoid applied on this HT minus 1 XT, which is this term coming here, right, into this W0 plus bias, right? So that is how OT we are getting, right? Okay. Now this OT, now this tan H is getting applied. Now you see this CT is going here as well as CT is coming here. This is CT, right? So we are applying tan H on CT. This tan H, pointwise tan H is applied on CT. Pointwise tan H is applied on CT, right? And then that is multiplied, pointwise multiplied with OT. So this is what you are getting, final HT. OT HT is equal to OT pointwise multiplied with tan H of CT. This is CT, right? CT going here as well as it's coming here, right? So HT is going out here as well as it's going out here. So that's the these are the simple equations of the LSTM. The point to note here in LSTM is how they are different from the RNN. So if you see, if we are able to what we are able to do, we are able to transmit the CT minus 1 as it is to CT, right? That means we are able to short circuit this, right. That means, though, if we have let's say a RNN, this RNN with LSTM units, a bigger, or RNN with LSTMs. So these all, if these all units are LSTM units, and let's say these are all LSTM units, right? So the problem with RNN was this long-term dependency, right? This Y, when it was dependent on this xi1, right, y4, let's say, right? So this long-term dependency was not getting not taken care of, right, in RNN. But in LSTM, I'm able to transmit this cell state. This is the cell state, actually, this cell state as it is to this, right? Because I can short circuit all of that. With this connection, right? With this connection. So that's the huge advantage of LSTM. I'm able to transmit this input to this output, and this output, or this cell state, is getting transmitted, as it is to this, right? So the long-term dependency can be taken care of in LSTM. So LSTMs were developed in 1997, in early or late 90s, pre-deep learning. So but they were huge, they had huge power, right?